The goal for a large part of Chapter 4 is going to be to prove that triangles are congruent, but before we focus on triangles, we can also focus on just any figures that are congruent. And by figures that are congruent, we mean they have the same size and shape, meaning that, yeah, if I also turn those, flip those, or slide them along my coordinate plane, it's not going to change the, again, size or shape of my figure. You might also see the term rigid motion for this type. Rigid motion is if this is also almost like a block of wood. I can take a block of wood, I can slide it. I can take a block of wood, I can kind of like flip it over what we call like a reflection line. I can turn it around, but what I can't do is I can't change, again, the shape or the size of that figure. We can also determine whether two figures are congruent if I look for a few things that we call their corresponding parts. So rather than just generally saying that congruent figures are going to have the same size and shape, we're just going to get more specific and talk about the geometric aspects of size and shape, and that's going to be comparing sides and also comparing angles. You want to think side length is going to preserve the same kind of size from one figure to another. If I change, again, like the length of a side, it's obviously not the same size. And if I change the angles from one to another, so again, if I have like an angle opening up wider in one figure than it is in this second figure, that would be changing the shape. So if I want to keep the sides and angles the same, that's going to keep my size and shape the same. We also want to make sure that when I name these type of figures, notice that we have a congruency name here, that this polygon ABCD going around in order around that figure is going to be congruent to, in that same order, notice, EFGH, so those corresponding pieces are going to match in that same order in our statement. And that also means that if I use the name itself, that's going to help me compare sides and compare angles, again, keeping the same size and the same shape. So if I look at like the first two letters of my first figure, AB, and I compare this first side, that's going to match our first side of our next figure. It looks like EF. So I know that the top of one and the top of the other will be matching, either just by comparing the pieces on the actual figure, so like both the tops, or I can just compare the first two letters of the name, and I know that those pieces will match. You can use the same kind of shortcuts for the next pieces. Again, if I look at BC and FG, middle two letters of each name, that's going to tell me that those sides are congruent. And also in my figure, BC, FG, that side kind of towards the middle of my shape, if it looks like this has been reflected over. And then if I compare again the last two letters, C, D, G, H, it looks like those would also be congruent. Matching on my figure, it looks like that's just the bottom part of each of those congruent polygons. And also I can even do something like match up last letter, first letter, last letter, first letter. So something like DA and HE would be congruent, just matching up that last remaining side that we haven't marked congruent yet. Trying hard to for congruency markings, but that would work. We can also match up, remember, individual angles. So like first letter, those angles would be congruent just based on that name. Second letter, I know that B and F are congruent. I know that C and G are congruent. I know that D and H are congruent. So we'd also be able to add in the markings for that as well. Kind of running out of space if you're trying to mark in all of those congruent. But yeah, the idea is that you could add those angle markings in, and whatever matches for an angle marking is going to be matching for my figure. So if we are given a congruency statement, like triangle WYS being congruent to triangle MKV, if I'm asked for congruent parts, remember we could just use the name itself and we don't even need a figure, but I think it's helpful if you guys are stuck to just kind of form a figure. It doesn't really matter what the triangle looks like, we're just told they're congruent. But notice if I am naming it in that certain order, WYS and MKV, I do want to match that same order if I'm trying to figure out congruent pieces. So it looks like W and M should be corresponding, looks like Y and R should be corresponding, or sorry, that's K. And then S and V should also be corresponding in those same positions. That allows me, just like that previous question, again, I could use the figure or I could use the name itself. If I want to match up the first two sides and the first two sides, or first two letters, I know that that would be a congruency statement comparing those first pair of sides, WY, MK, again, first two letters, or I can also just compare these sides of my figure should be congruent as a side. If I'm looking at the next two letters, so second two of each name, YS, KV, we should already know that those are congruent, so again, just based on the name itself. Or I could look at the figure and again see that if those matching sides were congruent, I also know that those are going to be what we call those corresponding parts. So last pair, again, if I match up the last letter and the first letter, I could call that SW, I could call that VM in that same order. And we can also see, just going around my figure, SWVM, that would be our bottom side that's also congruent. So remember, we have sides and we also have angles. If I was to match up those corresponding angles, again, same thing, we don't even really need the figure. We could just use first letter, if that name is correct for my congruency statement. I know that W and M should be congruent, and again, middle letter, Y and K should be congruent, last letter, S and V should be congruent. If I also want to check that back on my figure, I know that if I have those in the same position, bottom left corner, that top angle, and it looks like that angle in the bottom right, those are all in the corresponding position. So again, we know they're going to be congruent to each other. So our next problem, we're told that these two triangles are suggested that these two triangles should be congruent. And by using these two congruent triangles, we're looking for the measure of angle D, which is, again, not listed. We're given the measure of E, for example. And if I'm looking for the measure of angle D, we just need to know what would be the corresponding angle in that other triangle. We might be looking at this and say that, okay, I have a measurement for C, and that means that D should be 75. It is actually going to end up being that answer, but not for that reason. If we're looking at these matching triangles, again, A, B, C, and looks like D, E, F, if I was to match up the corresponding angles, D is actually corresponding to A. So I know that the measure of angle D, or I could say D is going to be congruent to A. And in that case, if their measures are the same, I would actually have to figure out the measure of A first, and that's going to allow me to find D. So if I'm looking for the measure of angle A, I know that I could add up those other two angles in that triangle, and I know that every triangle should add up to 180, so still looking for A. I know that if I add up those two and I get 105, I know that I can just subtract, and like I said, this actually does end up being 75 degrees anyway, because we have what we call an isosceles triangle. But as long as I found the measure of angle A, and D was the angle that was actually corresponding, that means I've also found the measure of angle D, and that's going to be that same measurement. That's just going to be that 75. So it is important, again, even though those two ended up matching, let's say if it was a 70 and an 80 instead, that is important to find that third angle because we know that D matches A. We don't necessarily know at the start of the question that D would also match C. So our third angles theorem is kind of common sense, you would think, but it's basically saying that if we have two angles that we know are matching in one triangle and they match two angles from another, then the only way we're going to be able to find that third angle is we just know it's congruent to whatever angle is left. So I think this also works with some actual values. Let's invent a couple of numbers for this. Let's say if A looks like is 70 degrees or so and B is, let's say, like 30 degrees, that means that if there was also the same 70 and 30 because we have congruent angles in my next figure, that means that the angle that was left, if I subtract those two from 180, leaves me with 80 degrees for angle C. And that means that the only way to finish that other triangle is also leave 80 degrees for angle F, meaning that C and F should have to be congruent as long as the first two pairs of angles are congruent. I can use that third angles theorem to prove, again, missing parts of my triangles. And kind of like with our last examples, if I have two triangles that we're given and we don't really have a diagram for it, I would just draw a diagram yourself and try to mark up. I think in a figure it's a little bit easier if we can actually see the information. But we're told, again, basically how our third angle theorem starts. We know two pairs of congruent angles from one triangle to another. We know that we have JKL as the first triangle, PQR as the second, which again, we don't know that the two triangles are necessarily congruent yet. But as long as I know that the first two angles match, so it looks like J and P are congruent, looks like K and Q are congruent, we're also told these as congruency statements. All we really have to do to apply that theorem is, again, just to say that the only way to form this triangle is to have those third angles that also match. So if the first two angles match, again, we know that the third has to. And I just kind of said something like this. You don't necessarily have to have that exact same reasoning, but essentially all we're doing is we're applying that third angles theorem to our triangles and knowing that, again, if the first two match, I know that the last one also has to match.